on to our next type of t-test. Now we are going to discuss independent samples t-test. So let's get into it. We're going to briefly review a one-sample t-test just to get oriented. We're going to talk about independent sample t-tests and the assumptions that have to be met to run independent samples t-tests. Then we're going to look at the sampling distribution of difference in means. It's a slightly different one, but it's still a sampling distribution. We'll talk about confidence intervals for mean differences, a Cohen's d effect size measure, and some independent samples t-test stuff in R. What are one-sample t-tests for again? Situations where you are comparing your one sample mean that you went out and collected to a known population mean. It is also when sigma is unknown, because if sigma was known, you would use a z-test. But what do we do if you go out and you collect two different samples, and you want to compare those two to each other? What do we do then? Independent samples t-tests. Now we are going to compare two sample means to each other rather than some population mean. So perhaps there's no known population mean for the groups of interest. For example, what is the average number of minutes per week that UT students exercise compared to students from St. Edward's? I don't think that there are statistics on this out there yet, but if there are, send them my way. Or maybe there's a new thing that we are measuring or a new scale that doesn't have established population means yet. So for example, is there a difference in the fidget score on the Fidget Assessment Battery 2, that's my scale, you should go and take it, between people diagnosed with ADHD and those not diagnosed with ADHD? So in this case, this new scale doesn't have any population means associated with it. I want to give it to a group of people who have been diagnosed with ADHD and those who have not, to then compare them. First, let's talk about some of the assumptions that have to be met so that you can do an independent samples t-test. One of the first and most important is that the observations are independent from each other, meaning there's no relationship between the people in the two groups. The next one is that the data are normally distributed, that they follow a normal distribution without any intense skews or crazy outliers, and this homogeneity of variance thing. So this means that both groups have similar enough variance. If one group has very small variance and one group has crazy large variance, it's not appropriate actually to test them with this particular test, but there are other options that we're not going to discuss here. And it's kind of a convention that if the ratio of the larger variance over the smaller variance is less than 1.5, it should be okay. For the sake of this class and all of our examples, we are going to assume that all of these assumptions have been met. But if in the future you take a more advanced statistics class, which I encourage you to do, you can run other tests to make sure that all of these assumptions are actually met. But again, for our purposes, we're going to assume that they are all met. Now, rather than comparing one sample to the known population, we are going to test the differences between two sample means. If we did this again and again, drawing samples and taking the difference between the first group and the second group, the differences between them over repeated samples will follow a normal distribution, thanks to that central limit theorem, and have their own joint standard error. Independent samples t-tests are typically two-tailed, but one tail is possible if there's already some evidence or some theory to show directionality. Here is independent samples sort of visualized. So there are some populations out there, population 1, population 2, that we take our samples from to then test the difference between them. So we have sample 1, sample 2. Take that difference, and if we collected and calculated those differences again and again, the average difference between the groups will be a normally distributed sampling distribution, as always. So what are the two different groups? Well, the two groups can be anything you want them to be. They're categorized by some sort of categorical or nominal variable. So we could do males versus females, mountain people versus beach people, side sleepers versus back sleepers, whatever you want. The two groups you choose to compare can be anything really, but you would hope that they should only differ on that one grouping quality, all else being fairly equal. So for example, male versus female, the participants should be of similar SES, age, and things like that. But it also depends on the research question and the participants available to you. Let's formulate some hypotheses. In this class, and for most comparisons between groups, the null hypothesis assumes a mean difference of 0, so no differences between the groups. So you could write the null hypothesis like this, with group A minus group B equals 0. So if group A was 10 and group B was 10, it would equal 0. The alternative for this, if you wanted to write it this way, would just be not equal to 0. Another way you can write it though is you can say that group A is equal to group B, and then the alternative would be group A is not equal to group B. And here are the hypotheses for our one-sided tests, but as I mentioned, a lot of independent samples t-tests are just two-tailed and they don't have an assertion of direction, so we're going to focus on those mostly in this class. So here's our independent samples t-test equation. I know it looks a little bit intimidating, but we're going to break it all down. And all t-tests follow the same basic idea that you have your sample, you subtract some sort of null hypothesis value, and you subtract by the standard error. So let's look into it a little bit more deeply. First, let's look at the null hypothesis part of this equation. So here is the null aspect of the equation. We have this mu of A minus mu of B. What do you think this is going to equal? Take a guess. Did you guess 0? So the null hypothesis for an independent samples t-test is there's no difference between the means. So if the null hypothesis is saying that A is equal to B, then it's going to be 0. So if we look at the original form of the equation, this thing right here technically is 0. You can set it to 0 and it kind of just drops out. So now we're left with this, which is a little bit more simplified. We got rid of one of those terms. Now it seems a little bit more manageable. And here we just have the differences between our two samples and the standard error down here. So here is like a sampling distribution again for like the null hypothesis. If the null were true, would you expect every sample of group A minus group B to be exactly 0? Why or why not? No, it won't be exactly 0 because as we've seen, samples are a little bit fickle. Because of random error and chance, the difference will not always be exactly 0. But just like before, we want to know a range of reasonable values that we can be 95% confident with, this kind of range of 0 enough. And if it's 0 enough, then we fail to reject the null and we conclude that there are no differences between the groups. But if it's not a reasonable enough value of 0, then we can reject that null hypothesis. Let's look briefly at pooled standard deviation, this S sub p thing. We rarely know the sigma squared for group A and group B, that's the variance, so we'll have to approximate it from our sample. Then we can combine these two sample standard deviations together to give us one measure of variation. Because if you have two groups, each one has their own variance, and they may not be exactly the same, and one group might have more people in it than the other. So we have to combine them using this formula here. I will not make you do this, but I do want you to understand what it is. And we can use this pooled standard deviation to calculate our effect size, Cohen's d. Now let's look briefly at the pooled standard error. I will also not make you calculate this, but you do need to understand what it is and how to use it. So here we have the variance for group A. We're going to divide by the number of people in group A, plus the variance of group B divided by the number of people in group B, and square root the whole thing. And this is our pooled standard error that we are going to use as our denominator in our independent samples t-test. Now, as always, we're going to need some degrees of freedom. So, because we have two sample groups now, we will have to update the way that we do our degrees of freedom. Now, instead of just subtracting 1, we are going to subtract 2. Why? Because we have two groups. And these are 3 different ways that I'm writing out the exact same thing basically, but let's go through them anyway. So this is the sample size of group A, minus 1, plus the sample size of group B, minus 1. Another way you could write that is group A plus group B, minus 2, or the big N minus 2. Big N is basically the total full sample size, not just one group and the other. So using these degrees of freedom, we're going to use the t-table in the exact same way, but now if you had, for example, 30 people total, 15 and 15 in each group, you would now have 28 degrees of freedom. But we'll have a few more examples of that shortly. Practice! Let's do some. All right, let's try this with some different diet methods. Let's say we want to find out which of 2 diets helps you lose more weight, a low-fat or a low-carb diet. So we're going to make 2 groups. One group will eat low-fat and one group will eat low-carb. There are 18 low-fat dieters and 14 low-carb dieters. After 3 months, the low-fat dieters lost an average of 8.2 pounds with a standard deviation of 2.1, and the low-carb dieters lost an average of 3.5 pounds with a standard deviation of 3.2. So, using an independent samples t-test, test if these 2 differences are significantly different from one another at the 0.05 level. Step 1, let's form our hypotheses. So our null hypothesis is that there is no difference between the means. Our alternative is saying that there will be a difference, meaning that one of the 2 diets you will lose more weight on. And this is a two-tailed test, as most independent samples t-tests are, because we are not assuming which diet is going to be more effective. Step 2 and 3, let's pick our level of significance, 0.05, because that's what the question asked us to do, and let's pick the appropriate statistical test, which is kind of easy to know because this lesson is about independent samples t-tests, so we're going to use an independent samples t-test. Now here is the original equation, but remember that this is just going to be equal to 0, because our null hypothesis is that the difference between them is 0. So this goes away, and we are left with this. We take the difference between the low-fat and the low-carb diet, and we divide by our standard error. Now let's go and get our critical values. We have an alpha level of 0.05. There were 8 people in the low-fat diet, 14 people in the low-carb diet. So we add both those together. We get 22 minus 2 equals 20. So we have 20 degrees of freedom. If we go and look on the table, we see that the corresponding critical values are negative and positive 2.086. Now let's visualize these cutoffs. If our test statistic is greater than the positive 2.086 or less than negative 2.086 or more than 2.36 pounds of difference, then we can be confident that the true difference between the samples is not 0 and we can reject the null hypothesis. So here we have the hypothesized mean difference, which is 0 under the null, right? Then we have our critical values here, 2.086, negative 2.086, and as usual I have translated these numbers into the raw scale again, so if the difference between the two means is more than this, or less than that, it will be significant. And this is how I translated those numbers. I take 0, which is our null hypothesis, and I add this margin of error to it, which is the critical t-value and the standard error associated with our problem. Step 5, calculate the test statistic. We take our sample mean for the low-fat group of 8.2 minus the sample mean for the low-carb group of 3.5 divided by this messy pooled standard error, and we get 2.56 is our t-statistic. Now let's go see if it's significant. Let's visualize some of these cutoffs and see where our test statistic falls. So here is our test statistic of 2.56, and it is certainly greater than 2.086. So we already know that we are going to reject that null hypothesis. And we can also see that in the raw scale, 2.9 pounds is further out than that 2.36. So they both tell you the same message. So if there was less than 2.9 pounds of difference between the groups, based on our sample sizes and the variance associated with them, it would not have been significant. Step 6, draw the conclusions. We kind of already have, but let's go through it again real quick. Our test statistic, 2.56, was far enough away from 2.086 that we can reject the null hypothesis. Now, we can also say the two diet methods are not equivalent. People lose more weight in the low-fat diet than in the low-carb diet. Here's the APA notation to write that out. You would have T, 20. We had 20 degrees of freedom because there was 22 people total, minus 2, 20. Now we have our test statistic here, 2.56, and our p-value was less than 0.05. Now if you're doing this by hand, this is what you would report, but if you were doing it in R, which I highly suggest you do, you can get the exact p-value, which is p equals 0.02. Now, go and construct a 95% confidence interval for the difference in the means. Are your results consistent with the hypothesis test? So this is a confidence interval for just one mean with our 1-point estimate. Now, to do one for the differences between means, we just take that difference, so group A minus group B, what was the difference between them? In our example, it was 2.9, plus or minus the critical t-value associated with the degrees of freedom times that standard error. So of course, this is our margin of error, and we're going to add and subtract that to that, and that is how we're going to figure out our confidence interval. It's just like we've been doing, but now instead of just one sample mean, it is the difference between two sample means. Here is our information. Now let's go plug it into the equation. We have 8.2 minus 5.3. These are the two sample means. Then we have the critical t-value we looked up in the table or in R. And here is that pooled standard error. You go through all that and calculate, and we end up with a confidence interval of 0.54 and 5.26. The relationship between confidence intervals and nulls is quite interesting. When constructing confidence intervals for a difference in means, the null hypothesis is again usually 0. So we can compute our confidence interval for the difference in means and check to see whether that interval contains 0. Because remember, the idea with null hypothesis testing is Is this a reasonable value? This sample mean difference, is it something that we would expect under the null? Is it 0 enough? Or is it different enough from 0 that we can actually conclude that this is not the null hypothesis and we can reject it? When the interval does contain 0, it's plausible that the difference between group A and group B is 0, which again is consistent with the null hypothesis and consistent with failing to reject the null. There's one way to interpret that confidence interval. If we take repeated samples of the given sizes and compute a 95% confidence interval for the differences in means each time, approximately 95% of the intervals would contain the true average difference in mean weight loss between the low-fat group and the low-carb group. Our 95% confidence interval suggests people lose at least half a pound and up to nearly 5.5 pounds more weight in the low-fat group compared to the low-carb group. Note again that this interval does not contain 0. So it seems that 0 is not a possible mean difference for the low-fat and the low-carb groups. So here's a visualization of the example we just did. Here is the null, and here is these light gray here and light gray here. This is the 0 enough range, that if it was around here, if it was only like a pound of difference between the two groups, that would still be considered 0 enough and still be in the null world and we'd fail to reject. Over here though, the orange 2 lines here, this is the confidence interval we put around our alternative. Now notice how this confidence interval does not contain the mean of the null. Now in this example, based on our hypothesis test and the fact that our interval does not contain 0, we get to reject that null hypothesis. But now let's look at an example of what it would look like if we fail to reject the null hypothesis. So let's pretend that our prior example was not statistically significant. So let's say we calculate a confidence interval that was negative 0.54 to 4.18. The first thing you should notice is that this contains 0, which means that 0 is a possible value. It's possible that the difference between the two diets is 0. So in that case, we would of course fail to reject. But we can also look at it over here. We see this gray line here and this gray line right here. This is that 0 enough range under the null hypothesis. And unfortunately, our sample mean right here is within that interval. You could also look at it the other way, and you could see that our interval for our estimates for the sample mean difference from 4.18 to that negative 0.54, you can also see that we have 0 in there. So basically, the confidence intervals are overlapping, which means we are not statistically significant and we fail to reject the null hypothesis. Again, to make it a little bit more clear, this red line here is the mean that we calculated for the difference between the two groups. And notice how it is inside of the null world. It is a possible value under the null hypothesis, so we fail to reject. Now let's look at effect size and independent samples t-tests. Independent samples t-test and effect size. So for these samples, the low carb versus low fat, our effect size is 1.01, meaning that the low fat dieters lost on average a whole standard deviation more than the low carb group. And the standard deviation here was equal to 2.86, which is very close to the actual difference between them, the 2.9. As we cover more and more statistical tests, it may become a little bit overwhelming, all these different tests being thrown at you. But the essence of all these t-tests is basically the same. You're going to take the difference between means, whether that be between two group means or between your sample and some known mean, and we're going to divide by some variation, that standard error, to get that t-value, which is a standardized value that we can then compare on our table and find out the probability of observing such a t-value. That being said, I have one more t-test for you, and this, because we've already had independent samples t-test, which means that there must be a dependent samples t-test, and that is what we're going to cover next. I will see you there. Independent samples t-test in R. Here's how you would calculate an independent samples t-test using summary data in R. First off, you have to tell R all the information, and there's twice as much because we have two groups. Then you calculate the pooled standard deviation using this equation. Then you calculate the pooled standard error using this equation. You then ask R to get your critical values using that QT function. Then we do our actual t-test, which is just sample mean 1 minus sample mean 2 divided by pooled standard error. Then we can get our margin of error by taking the critical value times that pooled standard error, and we can get our confidence interval by taking the difference between group A and group B and adding and subtracting our margin of error. This is all well and good, and if you want to use this to answer quiz questions, I highly encourage it, but let's look at some actual R data analysis with some real data. As you all know, there are a number of different majors offered at universities. Different majors result in different jobs and may result in different pay. Let's compare a few different majors and see if they are statistically significantly different from each other on their median level of pay. So here I'm reading the data, and you can find it on Canvas. Then I'm asking this table function. It's basically telling you all the different types of major categories that are out there, because I was just curious and trying to look at them all. Then I'm calling the library tidyverse, and this is the function that lets me filter for what I want. I say filter, the data set, which is college, and I'm telling it which column to filter for. So here, it's the major category, and I want the category to be equal to, and you put in quotes, the exact name of that category. So we have agricultural and natural science and resources and biology and life sciences. So now I have two new data sets that only contain those majors that are agricultural and natural resources, and another one that is just biology and life science majors. Now we have to state our hypotheses. The question is, do agriculture and biology significantly differ from each other in their mean income levels? Let's test this at the 0.05 level. So our null hypothesis is that they do not differ significantly. There is no difference in their median incomes. And the alternative is that they do differ, that one of them must make more money than the other. Now, before we actually run the test, I like to look at the descriptive statistics, and we can use a very nifty package called psych, and you use a function called describe. Here I am telling it to describe the descriptive statistics for me for this data set, the agriculture one, for the columns 4 through 11. And I'm doing the same for biology, and it gives us this. Tells us the means, the number of people, and the groups, and the standard deviations. Now, based just on the descriptive statistics, here is the mean of the median incomes. I know that sounds a little bit weird, but they had the median income for all the different categories, and they took the mean of all of those. So here we have 55,000, and for biology we have 50,821 and 43 cents. Now, if we just take the difference, we see that there's a difference of $4,000. Now, do you think that's going to be a statistically significant difference? Is it big enough? Let's find out. Now, to actually run the t-test, all you have to do is say t-test, parentheses. We call the data for the agriculture, and we use that little $sign to say, look at the median column. Then we get the one for biology, same thing, look for median. And then we're going to set the variance equal to true, which I will maybe explain at a later date, but for now, you can just do that. So here we have the output for our two-tailed independent samples t-test and R. We have 22 degrees of freedom, so there's 24 observations total. And we have this t statistic here of 1.63-ish. Before you even look at a table, do you think that's going to be significant? So that t-value was pretty low, and this p-value confirms it. The p-value is 0.1164, so the p-value is obviously greater than 0.05. We failed to reject the null hypothesis. The two groups do not differ. The confidence interval also confirms this. We see that the true difference between agriculture and biology in their median income is somewhere between minus 1,100 or plus 9,400. In other words, people who major in agriculture will make either $1,100 less than biology or $9,400 more than biology majors. Notice how the interval contains 0, so we know it is not significant. We can conclude that agriculture and natural sciences versus biology and life sciences are not statistically significantly different from each other in terms of median income. Let's try another one. What about business versus biology? Maybe agriculture and biology are really similar together. Let's try to pick something a little bit more different. So do business versus biology differ significantly from each other in their median income? Test at 0.05. Our null is that they do not differ. Alternative is they do differ. And we can look first at the descriptive statistics for the business majors and the biology majors, and we see that the difference between their median incomes is about $9,700, almost $98,000. Do you think that will be significant? It's definitely bigger than our last example, but is it big enough? Here is the output from our independent samples t-test. we can see that we have 25 degrees of freedom, so there must have been 27 observations. And we have a t-value here of 3.7526, which seems pretty high. Before we even look at the table or at the p-value, it seems like it's going to be significant. So let's see. Yes, indeedy. Look here at our p-value. It's 0.0009 something something rounded to 0.001. So our p-value is much less than 0.05, and we can certainly reject the null hypothesis, and we can conclude that there is a statistically significant difference. Now if we look at the confidence interval right here, we also see that that confirms it. We have a difference of 4,400 to 15,000, meaning that business majors on average will make somewhere between $4,000 to $15,000 more a year than a biology major. And notice that our interval does not contain 0, so it's significant. We can conclude that business versus biology are statistically significantly different from each other in their median income. Ding. Don't let that sway what you major in. Follow your hearts. Follow your hearts. And here is all of the code all together, so you can use this as a template, and I really encourage you to download this data set and practice a little, give it a go. There's a lot of other majors in there that you can play with and see if they are statistically significantly different from each other. I will see you in the next one. Bye.